I think we'll get started. So welcome everyone to part 3 of the session on emerging methods, strategies, and frameworks in climate engineering system interaction studies to support climate change adaptation and mitigation. There were 6 talks scheduled, but there has been a cancellation, but that's the last talk that was canceled, so it's not going to change the schedule at all. So as you all know, you've got 15 minutes, but ideally you should, your presentation should be for 12 to 13 minutes, leaving some time for questions. So our first speaker is Bernardo Tufel, and he's going to be presenting physically based deep learning framework to model intense precipitation events at engineering scales. You can share your screen, Bernardo.
Okay. There we go. And okay, cool. So the outline for my talk, I will first talk about my motivation for this work. I'm going to present my objective. I'm going to talk about the deep learning framework that I used to accomplish this, the climate model and simulations that I'm using to train my framework. And then I'm going to present some results in the way of emulation of select high intensity precipitation events, and also the reproduction of precipitation frequency intensity relationships. And finally, I'll present my summary and conclusions. So the motivation for this work is that intense precipitation events can lead to flash flooding, especially in urban regions, as you can see in the figures on the right. In terms of modeling, so a sub-kilometer resolution is required to capture these events accurately, because at coarser resolution we tend to underestimate the rainfall rates. But of course, with that high resolution comes very high computational cost, which is a major barrier in undertaking this engineering scale simulations. So the objective here is to develop a deep learning framework to model these intense precipitation events using coarser resolution data. And because it's deep learning based, it's data based, so it will have a much lower computational cost. So the framework that I'll be using is inspired by recent advances in video super resolution. So essentially, many people are working to increase the resolution of video. So here you can see one example. So on the left side, you have the low resolution image. On the right side, you have the truth. And in the middle is what this framework current video super resolution by Sayadi et al. Produces. So you can see it really captures some of the fine details in form of the branches and so on that you cannot really see in the inputs. So it is able to learn those. So essentially what our question was, okay, so why not do that with precipitation? So first I'm going to explain a bit about the framework that Sayadi et al. Used. So here in this figure, this is the framework. So the blue boxes are the low resolution information or the inputs. The green boxes are the output, and the red boxes are the convolutional neural network, in short CNNs, which is where the bulk of the computation actually occurs. So they essentially use the previous frame, so at time t-1 and at time t. So they use 2 consecutive frames to estimate the motion between these frames, like how is it moving. And they call this the optical flow. So they do that with this FNet, a neural network. So once they have the optical flow at low resolution, they just upscale it linearly to high resolution. They apply this flow to the previous estimate at high resolution. Then they transform this back to low resolution, input it into SRNet, which is another neural network, along with the current estimate at low resolution, and this will produce the new estimate at high resolution. So those are the results that you saw on the previous slide, and it's called recurrent just because then we take this new estimate and this becomes the input kind of for the next time step. So because they have two neural networks, they will have two loss functions. So one is on the loss itself. So they are trying to make sure that when we apply the flow to the previous frame, we get the current frame at low resolution. And then the more important loss is between the estimate from the model and the truth at high resolution. So in our study, we did some modifications to do this for precipitation. So one of the modifications that we did is we replaced FNet with an estimated storm motion, which we just derive from storm level winds, which we get from the model. So this is more physical than just trying to estimate it from the motion of precipitation itself. And the other change that you see is that we get rid of this block, and we work everything in high resolution. So that implies that we also need to first upscale the low resolution information here before passing it to SRNet. So what's the advantage of having just one neural network? First, we just have a simple loss function. So we are just minimizing the difference between the estimates of the model and the truth. And the other reason we eliminated like this conversion to low resolution is that we can now use any upscale factor that we want, which is important because we might do this work at many pairs of resolutions. So that was one of the reasons we did that. So just to give some technical details about this SRNet. So it's a 5-layer convolutional neural network. So it inputs the previous high resolution estimate affected by wind and the current upscaled low resolution. So the kernels are 3 by 3. Each of the 5 layers outputs 16 feature maps, and the activation function is the rectified linear unit. So the model that we are using is the GEM model. So we are running it at 250-meter resolution for 6 summers. So from 2015 to 2020. This is driven by coarser simulations, so using the same global environmental multiscale model at 2.5 kilometer resolution, which in turn are driven by the ERA5 analysis. Urban regions in the model at 250 meters are represented using the town energy balance model. It's important to mention that all convection parametrizations have been turned off at high resolution, and precipitation is output every minute. And why every minute? Because this is the lowest time step that we can afford, which is equal to the one of the 2.5 kilometers simulation. So here on the figure, you just see the model domain. So it covers the city of the island of Montreal and adjoining regions. So in red, you see the city, and blue the river, and other land covers. So the way that we train the model, so we have a training phase where the data from the 250-meter simulation is coarsened, and we use 4 of the summers of training data from 2015 to 2018, 1 year for validation, 2019, and 1 year for testing the model, 2020. And then in the predicting phase, we actually apply the trained model to the actual coarse resolution data. Okay. So these are some of the results that we get. So the first column will show you the low resolution input. The middle column will show what the framework is producing at high resolution. And the final column will show you the truth. So here, this is just select events. So you have one event on each row. So we can right away see that the framework is doing pretty good. It's able to capture most of these small precipitation cells that you see in the truth, which are, some of them are not really there if you look at the low resolution input. Same thing for this case down here, like some of the smallest details, like you can see here, are somewhat missed by the model, but it's still performing much better than the input data. So here I'm just showing a few more of these events. So you can see that it consistently performs quite good. You can also see, like in the low resolution, you might have like heavy precipitation right next to no precipitation, which doesn't happen in reality and which also doesn't happen in the framework. So it knows that the region of high precipitation is enclosed by regions of lesser precipitation. And here I'm just also showing you an animation of this, so you can see how the motion by the model is quite smooth, and it also follows the evolution of precipitation in the high resolution route quite well. You also see that there are no artifacts or no inconsistencies in this solution. So we can say that the deep learning based framework is able to produce realistic precipitation data, and it recovers a significant amount of the spatial detail. But when we want to apply it to the coarser resolution simulation, because both simulations have considerable freedom to develop their own precipitation evolution, the simulation at low resolution has higher autocorrelation in the spatial sense than the low resolution data that we used for training, which was created from the high resolution data. So you can see here that we have more autocorrelation in the low resolution one. So we want to correct this. So we do that by applying a sharpening kernel, sharpening filter, which is a 3x3 kernel, which reduces autocorrelation. So you see now here at the center, we no longer have this overestimation, and it also improves the precipitation frequency intensity relationship, as you can see here. We have the rainfall rate on the x-axis, minutes per summer on the y-axis. So you can see that the original data was the blue one. After we apply this filter, it's the red one, and the one that we're trying to emulate is the black curve. So we are getting much closer. And finally, to actually work at high resolution, when we actually apply the framework, these are the results that we get. So again, it's like the rainfall rate and the frequency. So again, the blue curve is our actual data at low resolution. The black curve is the high resolution truth, and the red curve is what our framework is doing. So it's getting very close to the truth, no matter if we look at the entire domain or if we look at a much smaller region. Like if we want to look just at the downtown core of Montreal, we're still doing quite well. So in summary, the framework that we develop can increase the spatial resolution of model precipitation to engineering scale. It realistically captures specific events and overall statistics. And because it's physically based, this framework can be easily transferred to a variety of resolution, periods, and regions. Thank you.
Thanks, Bernardo. Questions? So we have about, 1 minute, 1 to 2 minutes for questions. I don't see any questions. You can put questions in the chat, or you can unmute yourself and ask questions as well.
Hi, Bernardo. This is Iljo.
Yeah.
So you use the 5-layer neural network function. So how could we define the optimal number of layers? Because if you put more layers, then you might have more parameters that you have to estimate.
Yeah, exactly. So yeah, we would have to do, we didn't do it yet, but we can just kind of do a sensitivity experiment, so we can vary the number of layers. And at some point, the results won't improve anymore. So that would be kind of our optimal number of layers, because I'm also seeing one question in the chat from Charles Curry. So it's about the computational cost compared to a high resolution model. So kind of in the same sense, even if we use more layers, it's like thousands of times cheaper to run this machine learning model than to actually run the actual convection permitting model. Just for comparison, like running the convection permitting model, it might take about 14 hours just to run 1 month on about 1,000 CPUs, something like that. Here, the machine learning model, just to train it, it might take just a few hours, and we would just be using 1 GPU. And to do the actual predictions, once the model is trained, like we can use a few CPUs, and it's going to take a few minutes. So it's like really hundreds to 1,000 times more efficient.
Okay, so I guess we will have to move to the next presentation. And the next presenter is Francisco Casas. He's going to be talking about machine learning framework to aid climate model assessment and improvements. And Bernardo, you can take it from here. Francisco, you can share screen.
Hi, can you guys hear me?
Yes.
Okay. Good afternoon, everyone. Today I'm gonna present a new machine learning framework to aid climate model assessment and improvement using the case study of GEM simulated surface soil moisture. Okay, so the outline of the presentation is as follows. First, I'm gonna talk about the background on objectives of the research. Following, I will explain the different steps of the framework, datasets, and the specifics of the case studies. Afterward, I will focus in the models that we developed for the framework and the initial results. And finally, I will provide a summary of the main findings, recommendations, and conclusions. Okay, we know that climate model outputs are used in climate change adaptation and mitigation studies. In order to make these outputs credible, biases in the model must be understood and corrected. This process often requires a large number of sensitivity experiments, which is time consuming. And with increasing complexity and gaining spatial resolution of climate models, it is also very computationally demanding. In the last decade or so, the use of machine learning tools in climate science has gained attention as a means to reduce computational expense. And in this study, the main objective is to develop a random forest-based framework to identify potential mechanisms generating bias in climate model outputs of interest. Okay, moving on to the methodology, the framework consists of 2 steps. The first step is to develop a random forest-based emulator for the climate variable of interest. These models are trained on observed predictors that represent the mechanisms driving the climate variable of study. For those of you who are not familiar with random forest, it is a machine learning algorithm in which a number of tree predictors are combined. Each tree is built from a random sample of the training data, and the estimated value is the average of all regressed trees. This way, overfitting is reduced, and we obtain greater generalization capabilities. In step 2 of the framework, we replace the observed predictors with climate model outputs. The individual replacement of climate predictors aims to find its associated bias. And with this framework, we expect to identify the main drivers of bias of the variable of interest. Okay, for this study, we used 2 simulations from GEM to simulate the months of April to September over a 32-year period. As these are the most relevant months in flood studies, as I said, we ran two simulations. First one we labeled normal, since the geophysical fields intend to represent regular conditions to approximate observations. And the second simulation is designed to be heavily biased. And to this end, the vegetation was removed from the geophysical fields. Okay, here in the figure, I'm showing the simulation domain. It covers most of the province of Quebec. And for both simulations, the resolution is 4 kilometers and both are driven by Euro 5. Okay, now, sorry, now for some details on the framework. The development of the random forest models rely on the observation datasets to be as accurate as possible. In the case of this study, we used Euro 5 reanalysis data. 26 years were used for training the models, and 6 years were set aside for validation. The climate predictors related to surface soil moisture that we used are water availability, defined as precipitation minus evaporation, 2-meter temperature, relative humidity, snowmelt, and snow water equivalent. Additionally, topography, sand, and clay content were used as predictors. We developed two sets of models, a domain-based RF1 and a grid cell-based RF2. RF1 is a single model trained on the data for the entire domain, while RF2 is an array of models, one for each of the land grid cells. Okay, once the models are trained and validated, in step 2, we replace the climate predictors to estimate surface soil moisture. We replace them with outputs from the climate model. And the bias in each individual estimation reveals the underlying mechanisms driving biases. Okay, for the development of RF1, we use 12 predictors, each with over 33 million points. In the images, I'm showing surface soil moisture from Euro 5, which was used in training. 100 trees compose the random forest. Minimum leaf size is 1,000, and the impact fraction is 90%. And in these figures, I'm showing the results of the RF1 model. We can see here that there is a considerable amount of bias in both training and validation datasets. And these large biases can be explained as the trade-off between keeping large-scale features and capturing extreme values. To properly capture these values, a smaller minimum leaf size would be needed. However, the computational advantage of using machine learning models would be lost in case we did that. Okay, to develop the RF2 model, an array of models were trained. As I previously said, one for each land cell. Each model was trained with 9 predictors, each with over 4,000 points. The random forest contains 1,000 trees, minimum leaf size is 1,000, and impact fraction is 90%. Here are the results for the RF2 model. And as each model is trained on a limited range of surface soil moisture values, we expected a very small, here. We expected a very small bias in the training dataset. However, for the validation dataset, we see a small bias since the models never saw those values during training. However, the model is performing really good, and considering that these models have a superior emulation capability and that for this framework to work, we need the most accurate model, we selected RF2 to use in step 2. Okay. Okay, in step 2, we aim to find the causes driving bias. And to this end, we use the 2 GEM simulations that I previously presented. Here I'm showing the Euro 5 surface soil moisture values used both in training and validation. First GEM simulation has the normal geophysical fields. Second GEM simulation was designed to induce bias and therefore test the framework. And the framework's main assumption is that if a predictor is misrepresented in GEM, this will result in a significant drop in surface soil moisture emulation. And therefore, we will be able to associate that drop in regression with the bias of the predictor. Okay, moving on to the potential drivers of bias. Here, the plot in the middle shows the surface soil moisture emulation with all GEM1 predictors. And this is the bias in relation to the year of 5 emulation. We see a positive bias across the domain. In the top row, I'm showing the bias of each predictor. The plots in the second row show the bias between emulations once the predictor was replaced. Bias in water availability and relative humidity predictors from GEM1 lead to surface soil moisture biases with similar patterns. We can see that the bias in 2-meter temperature causes an opposite bias in surface soil moisture. So here we have a negative bias that results in a positive bias. And for these non-related variables, we observe a negligible influence on surface soil moisture bias. But we have to keep in mind that this study is focusing on the months of April to September. Yeah, this analysis suggests a strong influence of relative humidity in the northern region. We can see that here. While water availability and 2-meter temperature impact mainly the southern section of the domain. So we have that impact here for water availability and here for 2-meter temperature. Okay, moving on to the second GEM simulation. This simulation was designed to be biased, and we can observe a significantly larger bias when compared to GEM1. In that sense, the simulation was successful as all predictors have larger biases than their counterparts in GEM1, which in turn is reflected in surface soil moisture biases. We see higher biases in these plots. And larger biases in relative humidity point to processes impacting it, with vegetation being a significant one. Okay, next slide. In these plots, I'm showing where each variable is most dominant in the RF2 model. It was expected that water availability, here in blue, would be the strongest predictor in most of the domain, but we see an interesting result in relative humidity dominating the northern portion of the domain, while the same is true for 2-meter temperature here in the south. Another interesting result is that these three variables, water availability, relative humidity, and 2-meter temperature, carry most of the emulation bias. Overall, the emulation bias can be composed as the sum of the individual surface soil moisture biases. And the regional drivers of bias match closely the variables of importance analysis. So yeah, we see higher bias, for example, of relative humidity here in the north, where relative humidity is important in the model in the north. And same is true for temperature here, showing the impact, and yeah, in the almost the same regions where it's important in the models. Okay, for conclusions, random forest was shown to be an adequate method to model surface soil moisture. The proposed random forest-based framework, replacing observed predictors with model predictors, helped identify potential predictors responsible for bias in the variable of study, in this case, surface soil moisture. And these processes were also identified to have large influences according to the variables of importance analysis. Thank you. I want to thank Professor Laxmi Sushama, Compute Canada, Calcul Quebec, and the Canadian Space Agency for funding. I'll be happy to answer any questions.
Thank you, Francisco. So any questions for Francisco? So if we don't have any questions for Francisco, we can move to the next talk, which will be presented by Arun. So he will talk about exploring machine learning frameworks to fill the spatial and temporal gaps in satellite-based soil moisture and freeze-thaw data over Canada.
Okay, good afternoon all. Am I audible?
Yeah, we can hear you and see your slides. Yeah.
Okay. So my presentation is about exploring machine learning frameworks to fill the spatial and temporal gaps in satellite-based soil moisture data over Canada. So this is the outline of my presentation. First of all, the background and objectives of the work will be presented. After that, the methodology, that is the machine learning models to fill the gaps in satellite-based surface soil moisture data will be discussed. Two different machine learning models, that is random forest RF and convolutional neural network CNN, will be used in this study. And the details of these two models will be discussed here. After that, the results obtained with the two machine learning models will be presented and is followed by the summary and conclusion. Coming to background and objectives. In climate models, realistic simulation of soil moisture is important because it influences various mechanisms such as land atmosphere interactions, floods, etc. But soil moisture validation is difficult due to the lack of observations. So to this end, satellite-based observations will be useful, and nowadays satellite-based soil moisture observations are becoming increasingly available. However, over Canada, these satellite-based soil moisture observations has issues with spatial and temporal coverage. So machine learning models can be useful to fill the gaps in the satellite data, both in space and time. So now I will be presenting the different types of satellite-based soil moisture data used in this study. First of all, soil moisture and ocean salinity, or SMOS. SMOS provides surface soil moisture measurements globally from 2010 onwards with a spatial resolution of 30 to 50 kilometers. And it's part of European Space Agency's Living Planet program. So in this plot, the variation of SMOS surface soil moisture across Canada over 4 different seasons are presented. So the SMOS SSM values are averaged from 2010 to 2020 and is plotted here. So from this plot, it is evident that SMOS SSM retrievals are hindered by snow, dense vegetation, and water bodies. So during the winter seasons, most of the regions are snow covered, and due to that, the SMOS fails to retrieve soil moisture data from most of the regions, and wherever there are dense vegetation and water bodies are present, SMOS also fails to retrieve soil moisture data from that regions. Next type of satellite-based soil moisture data used in this study is advanced scatterometer, or ASCAT. So ASCAT provides the surface soil moisture measurements at a global level with a resolution of 25 kilometers from 2007 onwards. So it has been launched by European Space Agency, and this plot represents the ASCAT surface soil moisture variation across Canada over 4 different seasons, averaged from 2007 to 2020. So here also we can see the ASCAT ASCAT soil moisture retrieval is hindered by this type of dense vegetation, water bodies, and snow cover. So the objective of this study is to extend surface soil moisture values for SMOS outside of the available observation period over Canada using machine learning based approaches, and also to extend SMOS surface soil moisture values spatially if possible. So here in this study, we use ASCAT data as an ancillary data to validate the extended SMOS observation outside of their normal observation period. Now coming to the methodology, 2 different machine learning models are considered in this study, that is random forest RF and convolutional neural network CNN. So random forest is an ensemble learning technique that involves multiple base learners for the same problem. In ensemble learning, the estimates generated by the various base learners are averaged together to form the final estimate of the model. So the base linears in random forest model are the regression trees, and the estimates generated from these regression trees are finally averaged to form the final estimate of the random forest. So coming to convolutional neural network, CNN is a deep learning model, and it is used to recognize useful patterns from the input data. So it employs convolution operation to identify these useful patterns, and in convolution operation, multiple filters are applied over the input data to generate those patterns. So as compared to conventional machine learning models such as a random forest, CNNs are able to capture the dependency between predictors more efficiently. So this is the ML framework for CMOS SSM estimation. So it works in two stages. In the first stage, the two different machine learning models, that is RF and CNN, are trained using 10 years daily observed climate variables and geophysical fields from ERA5 reanalysis data as predictors, and the corresponding CMOS SSM values as the target. So we use data from 2010 to 2019 for training the models. So during training, some of the points from the training data set will be set aside as withheld points, and these points are excluded from the training process, and it will be used later to validate the two machine learning models. So to form the withheld points, some set of points are randomly selected from each time steps, and these points are kept aside, and these points are excluded from the training. So these are the set of predictors used in this study: ERA5 climate variables and ERA5 geophysical fields. In climate variables, we use evaporation, total precipitation, snow melt, snow depth, 2 meter dew point temperature, 2 meter temperature, and total precipitation minus evaporation, 2 meter temperature minus 2 meter dew point temperature. And for geophysical fields, vegetation cover and the soil type are the main type of predictors used in this study. So next, these two models will be validated. That is, RF and CNN models are validated. And for the first, we use two type of validation process. In the first step, using this trained CNN and RF model, the CMOS SSM values for the withheld period, that is 2020, will be predicted, and their estimates will be compared. After that, these two trained models will be evaluated based on the withheld points. So from these two type of evaluation, we will select the best performing model, and with that best performing model, the CMOS SSM values will be extended, and it will be validated with the available ASCAT data. So this one is the random forest framework used in the study. It takes inputs as the predictor, that is ERA5 geophysical fields and ERA5 climate variables, and from these input, k different bootstrap samples will be generated, and each of these bootstrap samples will be given as input to k different regression trees. So these regression trees will be act as the base linears for this random forest, and the estimates generated by each of these regression trees will be finally averaged to form the prediction of to form the estimate of the random forest framework. So these are the parameters of the RF model used. The number of regression trees is 200, and the number of predictors selected at random at each regression tree is 35, and the maximum tree depth is 40. So to find out these parameters, we evaluated the model using root mean square error for different values of these parameters, and whichever parameter is giving the lowest value will be selected as the final value for these parameters. So next one is the CNN framework used in the study. So the CNN framework used in the study consists of three parts: input layer, hidden layers, and output layer. So the input layer accepts the predictors, that is ERA5 geophysical fields and ERA5 climate variables. And from this input, the hidden layers will extract useful patterns, and using these patterns, these hidden layers will generate the surface soil moisture estimate, and it will be presented to the output layer. So mainly three hidden layers are used in this study. And each of these hidden layer contains 3 operations: convolution, non-linear operation by using rectified linear unit or ReLU, and max pooling operation. So convolution operation uses a set of filters to extract meaningful patterns from the data, and these 3 hidden layers works in sequential order. And finally, the meaningful patterns extracted from the given input will be given to the fully connected layer, and it will predict the surface soil moisture estimates, and it will be given to the output layer. So coming to the parameters of CNN model, we used grid search strategies to identify the optimal set of parameters. And it uses, in the first hidden layer, it uses 32 numbers of 7x1 filters, and in the second hidden layer, it uses 16 numbers of 5x1 filters, and in the third hidden layer, it uses 8 number of 3x1 filters, and we use Adam optimizer for training the model. Now, coming to the validation of the machine learning framework. First of all, the 2 different machine learning models will be validated using the withheld period. That is, the trained RF and CNN models are used to generate the surface soil moisture estimates for the year 2020, and the estimates are averaged over 4 different seasons and shown in this figure. So in order to evaluate which one is performing better, the biases associated with each of the trained models will be computed. That is, the difference between the RF predicted soil moisture and CNN predicted soil moisture from the real observation is computed and plotted here. So here it can be seen that both RF and CNN are able to capture the spatial and temporal variability of surface soil moisture, and it produces values very close to those of CMOS for most of the regions. However, compared to RF estimates, RF SSM estimates, CNN has less regions with bias, and also the estimates generated by CNN will be having smaller biases as compared to RF model. So we can conclude that CNN performs better than RF. Next one is the validation of CMOS SSM estimates for withheld points. So this figure shows the scatter plots of the true SSM values and the CNN and RF estimates generated, CNN and RF SSM estimates for the year 2010 and 2019 average over 3 different seasons. So here the blue points indicates the CNN estimates of SSM values, and the red one indicates RF estimates of the surface soil moisture. So so here also the CMOS SSM values are generally well captured, including the extreme values by the 2 different models. However, the CNN estimates are more closer to the diagonal line, and as compared to RF-based estimates. So we can conclude that CNN performs better than RF. So we will use CNN model to spatially extend the surface soil moisture values for CMOS observations. So next one is the data extension in time using CNN model. So this figure shows the extended CMOS SSM values for the year 2007 by CNN model with the ASCAT SSM value for 2007 as the reference. And here the small SSM values are averaged over 4 different seasons and shown in this figure. So here some important differences are noted for regions such as peatlands that were not available from CMOS data and therefore not considered in CNN training. So apart from temporal extension, some points are spatially extended also here in this. The differences are mainly due to the fact that these points are not available from CMOS data, and they are not considered for CNN training. So this one is a temporal correlation coefficient calculated between ASCAT and extended CMOS SSM values over 2007 to 2009, and is averaged over 4 different seasons. So the temporal correlation between extended CMOS and ASCAT data is high except for summer, and the difference in operating characteristics of the 2 sensors in the CMOS and ASCAT for certain regions leads to this low correlation for summer season. So next one is the spatial correlation coefficient between ASCAD and extended CMOS SSM values over 2007 and 2009. And here also the spatial correlation between extended CMOS and ASCAD data is high in summer, which confirms the same trend as that of temporal correlation. So coming to the conclusion, two different machine learning models are investigated in this study, that is RF and CNN model to estimate CMOS SSM values. It has been observed that CNN-based model has better performance in estimating CMOS SSM values. And also CMOS data extension in time seems to be reasonable, but need more caution when filling it in space. So work in progress to integrate other SSM data, that is SMAP and AMSR, to develop a more comprehensive data set for evaluation. Okay, that's it from my end.
Thank you, Arun. So any questions from the audience for Arun? Okay, so I see one question. So which predictor do you think is the most important for simulating soil moisture? And could we exclude some correlated predictors?
Yeah, actually the importance of predictors are not computed yet in predicting the soil moisture values that I have to do.
Okay, so if there are no more questions, we can move to the next talk. So the next talk will be presented by Khalil Hashem. So he will be talking about super resolution climate and tailings pond modeling for the Mount Wright mine.
Can you see my screen?
Yep.
Okay, great. Good afternoon, everyone. My name is Khalil Hashim, and my presentation today is about super resolution climate and tailing pond modeling for Mount Wright mine, which is a part of my research as a PhD candidate at McGill University. So the outline of my presentation for today is as follows. First, I will present background information and the objective of the research. Then the methodology will take place, including super resolution climate modeling for Mount Wright mine and the application of tailings erosion due to wind-induced waves and currents. After that, I will present the preliminary results of this study, and finally, conclusions and future work will take place. Starting with the background information, each mine goes through a life cycle that consists of different phases and components. That is the development phase that includes the mine design, infrastructure, and logistics of a mine. The operation phase that includes fragmentation of the ore, the materials handling systems, and many other components. And finally, the closure phase, which is the last phase of a mine life cycle and includes managing the tailings storage facility and site remediation. These phases and components can be directly or indirectly impacted by different climate variables, such as precipitation, wind action, the active layer thickness, among many others, especially in the northern regions of Canada. For instance, the muck and hole system, which is a part of the materials handling system, can be impacted by changes in soil moisture and precipitation, as they directly affect the rolling resistance of the mining trucks. Also, the tailing management facilities can significantly be impacted by different climatic factors, and it will be discussed in more details in this presentation. Such impacts needs better quantification. However, there is a lack of climate simulations at a fine resolution that is important for the engineering applications, including the mine and its tailing management facility. So as for the tailing management facilities, first, tailings are defined as the byproducts and wastes that is generated by the mechanical and or chemical processes after extracting the desired ore from a processing plant. And in general, tailings can impose several risks that can impact the human health, the infrastructure, and the environment if not managed properly. For instance, there was arsenic leakage from the giant mine tailings, and it happened mainly due to the permafrost degradation. And as we can see from the figures, the figure on the left-hand side, thermosiphons is being used as an adaptation strategy to freeze and seal the tailings and therefore prevent the leakage. Moving on to talk about Montrite mine, and as we can see from the map on the top right-hand corner, the mine is located in northern Quebec, and it's one of the biggest iron ore open pits in the world and the largest in Canada. And currently, it has Paul's Peak pit as the only active pit at Montrite mine, and the operations will continue till the year 2045. Also, the existing tailing management facility at the mine will be used to co-deposit fine and coarse tailings till the year 2045. However, the tailing management facility can be impacted by different climatic factors such as the wind causing internal erosion, as well as extreme precipitation causing flooding. And therefore, we aim to study Montrite's tailing management facility using super resolution climate simulations that's being developed. Moving on to the methodology, the climate model that is used in this study is a modified version of the global environment multi-scale GEM model. And to perform super resolution climate simulations, deriving data from 4-kilometer resolution climate simulation covering most of Quebec, as we see in the domain with the blue border, is fed into a 1-kilometer resolution climate simulation for the domain with the red borders, and deriving data from the 1-kilometer simulation was used for the 100-meter resolution climate simulation. And also, it is worth noting that the 4-kilometer simulation was driven by ERA5 dataset. The 100-meter domain over Montrite consists of 380 by 340 grid cells, and the grid is shown every 20th grid point. Also, SRTM digital elevation model at a 30-meter horizontal resolution is used for this simulation. The outputs from the climate model will be used to assess the tailings erosion rate, where the erosion rate is a function of the total bed shear stress and the critical shear stress of the tailings, where the total bed shear stress is the stress on the tailings surface due to the waves and currents induced by the winds, and it depends on the wind magnitude, the water cover depth, and the pitch length over the tailing pond. While the critical shear stress is a function of the tailings properties, including the unit weight and the particle size distribution of the tailings for the site specific. Moving on to the preliminary results, the Landsat surface temperature dataset was used to validate the climate model outputs. The data is available at 30-meter horizontal resolution, and it was interpolated to 100 meters to allow comparison with GEM 100, which is the model simulated at 100-meter resolution. Landsat data is the best publicly available data to be used to validate GEM 100 outputs for the surface temperature for the studied domain, where the satellite collects the data between 3 and 4 p.m. GMT, and the data is shown. The data shown in the figures represent the winter, fall, and spring seasons. Also, it is worth mentioning that the Landsat data used was filtered to include the cloud cover only between 0 and 5% to avoid invalid data due to clouds. As we can see from the results, the mine and the tailing management facility are both resolved in the Landsat and GEM 100 outputs. And looking at the biases, we can see that the model performs reasonably well with a bias in the range of 1.5 degrees Celsius for most of the studied domain. And the slight underestimation near the open pit and tailing management facility is caused by the heat generated by the mining operations that is not being considered in the model. Comparing the wind magnitudes for the summer period between GEM 100 and GEM 1, which is the model simulated at 1 kilometer resolution, we can see that the wind magnitudes are more representative at 100-meter resolution, resolving the mining area and the tailings management facility as marked in the figures. Also, it was noted that high wind magnitudes are presented over the open pit and its tailings management facility, reaching more than 12 meters per second, which can be a great influence causing erosion within the tailings management facility. Also, the dominant wind direction at high wind magnitudes is the northeastern direction for both GEM 100 and GEM 1, resulting in having a pitch length over the tailing pond between 1,200 meters and 1,400 meters. Looking at the shear stress values at the tailing surface, we can see that the results using GEM 100 outputs turned a higher stress values when compared to GEM 1, where it reaches 0.5 Pascal using GEM 100 outputs and only 0.35 Pascal using GEM 1. And regarding the critical shear stress of the tailings, and based on Montrice tailing properties, which is D50, which represents that 50% of the particles are larger than 50% of the particles are larger than 0.255 millimeters, and the unit weights of Montrice tailings, which is equal to 2,400 kilogram per meter cube. The critical shear stress was estimated to be 0.164 pascals. And feeding these shear stress information into the erosion rate application, it turned out an erosion rate up to 0.5 gram per meter square per second using GEM 100 outputs. However, the erosion rate estimate is almost zero when using GEM 1 outputs, and this is due to the lower wind magnitudes presented in GEM 1 at water cover depth equals to 1 meter. And also, it is worth mentioning that the tailings erosion can have significant impacts, including high tailing oxidation rate and higher erosion at the dikes that can contribute to breach in the tailing management facility. So to sum up, tailings management facilities are vulnerable to different climatic factors as they contribute to breaches in the tailings dams and therefore cause significant damages to the tailing management facility. Also, when simulating GEM model at 100-meter resolution, the wind magnitudes seems to be more representative when compared to 1 kilometer, turning out higher bed shear stress and erosion rate values. And regarding the future work, it can include validating the GEM outputs at 100-meter resolution against site observation collected from the mining site. And also it can include assessing the tailing management facility, including the erosion rate and also exceeding capacity under future climate using GEM outputs future projections. Finally, I would like to acknowledge and thank Miguel, Tyson, ArcelorMittal Company, FQRNT, Compute Canada, and Calcul Quebec for their support for this research. Thank you, and I'm ready to take any questions.
Thank you, Khalil. Do you have any questions from the audience? Okay, if there are no questions for Khalil, we can move to the final talk of the session. So this will be presented by Yvonne Kim, and she's going to talk about nature-based solutions for urban flood mitigation, perspectives on emerging technologies.
Thank you, Bernardo. Can you confirm if you see my slideshow?
Yes, we can see it.
Okay, great. Hello, everyone. My name is Yawon Kim. I'm assistant professor in the Department of Civil and Environmental Engineering at Carleton University. So today I'm going to talk about nature-based solutions for urban flood mitigation, some of the perspectives that we learned from the survey and then from the literature review for our five-year project. So this is something more, something that's softer than the machine learning that we've heard so far. And before I start, I want to thank Dr. Navid Khalik, who is my research collaborator at the National Research Council of Canada, and undergrad student RAs who participated in this project, Bryn, Shivam, and Abby. So many of cities around the world are located in areas relatively high climate hazard, along with coastlines and rivers, which are water stress regions. And as human population and built infrastructure are densely aggregated in urban areas, cities are especially vulnerable to extreme weather risks like flood, droughts, and heat waves. And adverse impacts of climate hazards of floods, heat droughts, in cities are likely to be exacerbated due to the complexity of anthropogenic changes in urban environments, which are projected to increase both in frequency and magnitude. And although each city faces a unique combination of climate change related challenges, flooding has become the most widespread and costly natural disaster across Canada, and it is likely to be one of the most impactful weather events that will cause climate related infrastructure damages in Canada in the coming years. And many of you might be familiar of this devastating flooding event happened in Ottawa-Gatineau area. The left picture shows the flooding event happened in 2017, which led to mandatory evacuations in the affected area and flooded over 5,000 homes in Quebec area. And the city experienced another major flooding event in 2019, as you can see on the right here. The flooding not only causes physical damages to infrastructure systems and buildings, but it also incurred socioeconomic damages such as business disruptions and loss of homes, as well as ecological damages such as habitat losses. So recent climate studies find that extreme weather events are driven by changing climate variability and more greatly due to human activities. And although we cannot predict a specific weather events at a certain point of time in the future, advancements in climate sciences made us possible to understand how much a weather event has been intensified or weakened due to climate change from the historical observations, such as the observed changes in the occurrence of heavy precipitation events, as you can see in this slide. And in addition, projection of future climate tells us that the recent trend towards the increased heavy precipitation events will continue in the future. So climate change is expected to result in shifts in the location and timing of rain and snow across Canada, and the intensity and frequency of floods are projected to increase. As temperature rises, warmer air can hold more moisture. Therefore, in a warmer world, the hydrological cycle is expected to become more intense, with more rainfall concentrated in extreme weather events and longer dry spell in between, which can increase the impervious rate in urban land covers. And at the regional scale, these changes in climates are expected to cause streams to shift from nival flooding, which are snowmelt dominated, towards pluvial flooding, which are rainfall dominated regimes. And for example, climate change played an important role and critical role in the extreme rainfall events that contribute to the 2013 Calgary floods, the 2014 and the 2017 Ottawa floods, as you saw in the previous slide. And the challenge of urban areas in this changing climate trend is that infrastructure systems that are designed to protect the city from climate risks are still failing and causing damages in urban areas. As you see in this picture, cities have built and upgraded infrastructure systems such as the levee in New Orleans and the storm drainage system in Houston, following the engineering design criteria and calculated risks. However, these systems have failed responding to extreme weather events, even with the advancements of engineering design practices and climate science. And I see the biggest impediments to design and management of those conventional infrastructure systems are not just a lack of technological solutions, but also an incomplete understanding of vulnerabilities within the urban systems that encompasses social, ecological, and technological system domains, and the difficulty in, and also due to the difficulty in choosing the most appropriate solutions for resilience and long-term sustainability. So current infrastructure development practices have been remained largely unchanged in the past several decades. And these robust traditional infrastructure systems have been designed to be large, gray infrastructure systems to be with low probability of failure and to last for decades, and they are often oversized to comply with the safety margins to avoid any possible failures. However, those traditional infrastructure design practices are rigid and do not reflect the changes in the profile, frequency, and the intensity of extreme weather events, and it makes the rehabilitation of infrastructure system to be more difficult in urban areas. So therefore, as going into the future, urban infrastructure role isn't just limited to utilizing resources and providing public services like we did in the past. More recently, an important role of infrastructure system in urban area is to provide protection from climate hazards like extreme rainfall and heat that I mentioned earlier, and also to mimic the natural systems to minimize the environmental perturbations. Excuse me. So, and there is this emerging concept of safe to fail design for infrastructure systems that is the opposite concept of the current infrastructure system, which are designed to be fail safe and to avoid failure. And the safe to fail concept stemmed from three study disciplines, as you can see in this slide: resilience engineering, safety science, and urban planning. And here I'm going to focus on urban planning and the green infrastructure systems and nature-based solutions approaches to deal with this infrastructure failure. These urban planning approaches in infrastructure design emphasizes that small-scale design innovations with expectation of minor failures. So so the failures in this sense is an experience that can be naturally observed in the ecosystem and ecosystems. And specific examples that demonstrate these perspectives are green infrastructure and low impact development practices such as biosales and urban tree canopies. And another important perspective in thinking about designing infrastructure systems going into the future is the urban nature. The urban nature is a potential source of solutions to the compound urban climate challenges presented by urbanization and climate changes. So nature-based solutions, which are sometimes referred to as green infrastructure, ecosystem-based adaptations, or urban ecological infrastructure systems, are increasingly being implemented in cities to promote public health and safety, enhance livability, promote equity, and restore natural hydrologic cycle and ecological processes. And the effective implementation of nature-based solutions often associates with the integration of social, ecological, and technological system domains and elements and their processes. So for example, in a coordination of the social and technological domain, it involves with the construction and maintenance of nature-based solutions, accessibility to those solutions, and service delivery. In the ecological and technological system domain, it's involved with the hybridity and functionality and biomimicry of the nature-based solutions. And in the social ecological domains, it often associated with which ecosystem services are delivered by nature-based solutions and how to be provide those services, and then how to manage those nature-based solutions that are being implemented in cities. So from the survey that we conducted through an international network of 35 research institutions and academic institutions, as well as business and government agencies, which is called Nature-Based Solutions for Urban Resilience in the Anthropocene. We had a survey of what researchers and what practitioners think about are the most important nature-based solution analogy gaps for urban resilience. And some of the findings tells us that it is important to understand the provision of ecosystem services in the perspective of interactions of social, ecological, and technological domains, as well as how to assess the effectiveness, synergies, and trade-off of nature-based solutions with the existing infrastructure systems in urban areas. And some other important knowledge gaps that we need to focus on is equity issues that the NBS brings into the urban areas, and some of the an important role of natural ecosystems. So here I'm going to more focusedly talk about what are some of the examples for nature-based solutions to mitigate the inland and urban flooding. So according to the EPA study of 20 watersheds that are projected to grow between 2020 and 2040 due to increased precipitation and development, using green infrastructure to mitigate the flooding from storm drainage systems can save hundreds and millions of dollars. However, these solutions, the solutions a community can employ depends on its specific locations and existing infrastructure and the type of flooding that it faces. Either they are riverine, or they're storm drainage systems, or that is caused by runoff events. And so all the potential solutions should be evaluated in context of before being implemented. And some of the solutions, green infrastructure and nature-based solutions for flood mitigation includes green roofs, rain gardens, bioswales, urban tree canopies, and permeable pavements, which all helps to reduce the urban runoffs that are generated from the stormwater. And another type of infrastructure, nature-based solutions that can be often implemented, and they're increasingly implemented in urban areas, is natural infrastructure, which uses existing or rebuilt the natural landscapes that exist in urban areas, such as urban forests, floodplains, and wetlands, to increase the resilience to climate impacts, and it often results in environmental, economic, and social co-benefits. So restored or constructed wetlands and marshes are some of the examples, as well as riparian buffers. And what I want to also emphasize is that nature-based solution is not just the green, not just focusing or not just emphasizing the natural systems that exist in urban areas. Some of the more technologically focused solutions, which are porous pavements and bioswales, can be also nature-based solutions that mimic the natural cycle to reduce the impacts of climate risks. And here I'm going to wrap up with mentioning some of the co-benefits and challenges of nature-based solutions for flood mitigation. Some of the co-benefits are, it is cost-effective, and it provides habitat restoration and protection, and supports some other benefits like recreational commercial purposes. And some of the challenges are the maintenance and scaling up the solutions to deal with larger scale risks. So here, in collaboration with the National Research Council and with Carleton University, we are in the process of a 5-year project to develop a national guideline for NBS for urban flood mitigation. And we're going to test out different nature-based solutions in different urban contexts in the Canadian regions to understand, how they can be implemented to mitigate the urban flooding. So that is summary of my presentation, and I'll be happy to take any questions.
Thank you, Johan. So, any questions from the audience?
Excuse me. I have a question for you, Juan. So you mentioned that you will be testing these different nature-based solutions in different parts of Canada. So are you going to be doing numerical simulations, or what is your approach going to be like?
Yes, so we're going to first we're going to mimic the urban drainage systems in the with the hydrological modeling to understand what's the current status of infrastructure systems in urban areas. So we have potential 3 cities that we are going to test out, model the drainage system of the urban areas, and then we're going to force some of the rainfall, snow/rainfall precipitation scenarios into the model to understand, what are the flooding potentials in these areas, and then we're going to also model into the system to some of the potential nature-based solutions and understanding how they might reduce the flooding intensity in simulations. Yeah.
Could I ask a following question?
Sure.
So in your opinion, which models are the best ones, to test these nature-based solutions? I suppose it's very limited.
It is very limited.
Yeah,
exactly. It is very limited, especially to model the urban watersheds. We have very limited kind of options because they are really complex to be represented, and there are few options to do. Our kind of most top consideration right now is using the PC swim, which many researchers who studies urban flooding uses to understand our urban watersheds. Yeah.
Okay, thank you.
Great. Any other questions? Okay. If there are no more questions, we can bring this session to a close. So I want to thank all the speakers again, and also thank you to the audience for staying with us, and have an excellent rest of your day.